Well, howdy, physics sleuths and inquisitive souls, and welcome to Dynamic Gravity. So, on this lesson, there's a few things that I hope to teach you today that might serve you well in your life. And we are going to end with a grand epiphany about gravity itself, which no one has ever realized before, including myself, until just recently. We've pretty much gone as far as we can with this thing, with our current levels of knowledge available. Everywhere, every direction we go, we start running into walls, impassable walls that have been erected by Mother Nature herself. And what do? You can't go through the wall. It's the whole purpose of the wall, is you can't get through it. So we could give up and go home if you're not up for it. I'm hoping you are, though. I know I am. So a technique that I have found has worked very well for me is rabbit hole deep diving, I like to call it. You have a wall in front of you. Cool story. There's always a way around it. For every vice, there's an anti-vice. And if Mother Nature puts a wall in front of you, she has a way around it, for herself at least. Hence the rabbit. Rabbits got to go where a rabbit's got to go, and they dig their little burrows, and it comes out here and there. And some rabbit holes are dead end, and some rabbit holes take you right to where you want to go. So, we are going to start going down rabbit holes in this channel, and so we can learn some deeper knowledge. Let's get on with it. So, as always, we start with Newton's theory of gravity, right? Very simplistic. Moving on to Einstein's theory, much more complicated. He, he added a bunch of variables in there and then tried to figure out what was going on the best he could with the math that he had that he knew worked. And, he came up with this whole space-time thing. And, it's not a bad ideal. It's just there's no evidence of it. We can't find any evidence of space-time. So I don't put too much faith in anything Einstein says. I do put faith in his math, though. His math does work to a certain level, to a certain degree. Also, I'd just like to say, if you guys have no clue what I'm talking about, dynamic gravity is your first time here or whatever, and the details for this video, I will leave a link to a paper I wrote that describes everything regarding dynamic gravity. If you read that, I'm sure you'll be 100% on the level. So, I highly recommend that if you haven't already. All right, so we got Einstein, all right? And, he came up with this very elegant-looking equation, which is just a damn mess. Just an absolute mess. These are all tensors, matrix, tensors, metrics. It's just there. And he had to come up with his own little constant. Einstein's gravitational constant. Like Newton. It's nothing like Newton, dude. It's nothing like Newton. A lot of mainstream general relativity lovers or fanboys will tell you that this equation here, or this constant right here, is the stiffness of space-time. That's what this represents, and that's what Einstein wanted to represent. And you see, it's a very, very small number because it's got to the fourth power of the speed of light on the bottom, on the denominator, whatever. So this is insane. Like, this is an insanely small number. And you're like, what the hell is going on, dude? I thought this was supposed to cancel out to Newton's theory under normal circumstances. How is it going to do that when Einstein says the force of gravity is actually, instead of to the 11th order of magnitude, to the minus 43rd magnitude of order? It doesn't make any sense, right? But this is how he does his math. And I'm about to explain what is up with this number. It's not what they say it is. It's not the stiffness of space-time. That's all bullshit. Anytime anyone says it deals with space-time, they're full of shit. They have no evidence to back up their claims. Just this formula that works out, and they want to try and make sense of it, but they can't because they don't understand what it is. So, we got this, right? Let me see. Is it down here? No, it's not. Anyways, remember this number, kiddies. 8 pi g divided by the speed of light quadrupled. So, if we go over to a metric tensor, which is what all of these are, this little UV says it's a tensor of this or that. As you can see, every single thing here is a tensor, except for, of course, this lambda, the cosmological constant, which Einstein just threw in there willy-nilly once he thought that the universe, wasn't going to be crunching back in on itself. He thought it was static, and the only way to prevent that is throw in some sort of anti-gravity. But there is no anti-gravity in Einstein's general relativity. It doesn't exist. So he threw in this cosmological constant and said, well, maybe this is everything, space itself, just expanding or something. I don't know. Figure it out. Cool story. So here's the problem with metrics, tensors. They are ugly. They are not an efficient way to do math. That's why whenever you just, if you do metric tensor math, you just cringe every time you see it because it's so inefficient. Like half of these cancel out because they're the opposite of each other, and you're left with usually just the middle row or something. Well, Einstein's equation only works if you have a metric that defines the body of gravity that you're looking at. And the most commonly used one, from what I can tell, is the Schwarzkopf metric. So if we go down here, here we go. Here's a Schwarzkopf metric, all right? This came up to be used in Einstein's equations, all right, specifically for that. Now, this is said to calculate the event horizon of a black hole or something. Whatever, I don't know about that, but we'll see. But funny thing here, if you look at this, you see this is kind of absurdity. The Schwarzkopf metric, as you can see right here, here's the tensor, or the metric, being written down, and you see it's written twice, right? So these are going to be times each other, okay? And this is an angle or whatever, describing how much of Einstein's force of frame of reference is going to be applied to Newton's equations. But so we got 2gm and r times c squared. So we're going to times this together, and now you're going to have like 4g squared times m squared divided by r squared over c to the 4th power. But because it's on this side of the equation, and here we go. Yeah, I think it's over here is where the Schwarzkopf metric is going to be. And Einstein's k value is right here. So as it crosses the equal sign, it's going to flip. It's going to invert itself. So what's really happening is Einstein threw in this number right here to cancel out the ridiculousness of the Schwarzkopf metric right here. So you're going to have c to the squared times r, or c to the cube times r to the squared, right? Well, the r to the squared, as we know, has to be there somehow for Newton's equation. And the c to the 4, well, that's going to cancel out. So this whole number disappears. It's like that. Now you got g squared and 4. So 4 is going to take this down to like what, 2? Yeah, 8 goes to 2 now, much more reasonable. Pi, I don't know where that comes in. It's somewhere that's going to get dealt with, I assure you. Is there a pi here? I don't see a pi here. There's a pi somewhere in the equation. He's going to have it probably over here for the energy tensor, would be my guess. It's there somewhere, trust me. And then we got g squared times m squared. Well, you got to have the m in the equation because m times m, of course, these are different masses. So I'm not 100% certain. You got to have supercomputers to work this out. That's, one of the problems with Einstein's theory. So I've never been able to work this out, unfortunately. I can't tell you exactly every step where everything disappears away. But I can assure you that this m and this m, it could be the different m's and different masses, probably, which means now we're right back to here, only we got 2 g's instead of 1, but we got 1 g on top and 2 g's on bottom. It's going to cancel out to 1 g. So now we're right back essentially to Einstein's equation. The only difference is there's a 2 in front of it. I'm sure that will cancel out somewhere as well. Look, there's a 2 right here that could cancel that out. Who knows? It's all gonna cancel out to this equation. I promise you, under normal conditions, that don't involve massive time dilation or a massive gravity field or something along those lines. Excuse me. Brain damage from the war. Apologies. So that's the deal with this. This is not the strength of space-time, okay? Maybe the general relativity fanboys won't interpret it that way, and maybe in a certain perspective they're right. I don't know. But what this was created to balance off the metric that had to be used to define the gravity source. And it's the only way it can work out. These have to equal out and cancel out somewhere in the equation, or it will never revert back to this, which we know is by far the law on how gravity works. So that's the first thing, is getting a little deep here into how Einstein's equation works with this constant, with Einstein's constant, what's going on here. So now moving along, there was a gentleman, Poisson, long time ago, who created an equation that described, like, electric charge, mass density distribution. So this deals with the EM force, all right? This is what his equation deals with. Well, Poisson figured out that he could also apply this equation to gravity, to a gravitational field. And so he did. And what he came up with, this is considered Newtonian gravity, not relative, or maybe it's relativistic, but it's not general relativity. It's Newtonian. And this is the equation right here, pretty much. And you see, he's also got a 4 and a pi in there and some weird numbers. This p, I think, is density or mass density or something. This can all cancel out to essentially g if you really want it to. But yeah, so Poisson basically calculated sort of like the same way Einstein did. He kind of did the same equations and finagled them, with Newton's equations too, but in a different way, not accounting for the same things that Einstein's equations account for. But this equation, Poisson's Newtonian gravity equation, will give you essentially the same numbers as a space-time distribution, of gravity, a gravity well, that you would say, well, that's created by space-time, a gravity well. Cool. Poisson says it's not. So now we got a conflict here. We got two answers. They're relatively the same, but we got two completely different theories explaining what's going on, even though the math is ultimately pretty similar. What's going on with that? Maybe we can figure this out. So, this is very interesting, right? So, there's a reason, I'm jumping ahead of myself, there's a reason why Poisson was able to manipulate Newton's equation and run it as he did his equation, which deals with the electromagnetic force. That should give you kind of, guys, a little hint, since dynamic gravity is all about the electromagnetic force, not space-time. Kind of interesting, he can apply these equations the same. Well, the reason why he can do that is because a gravitational field conserves energy. So basically, if you have, what that means, if you have 2 points in a gravitational field, it doesn't matter what path you take to get from one point to the other. As long as you know where this point is and what's up with that, and where this point is and what's up with that, the equations are all going to give you the same number. The same amount of energy is needed to go from there to there. Whether you go up, down, straight, it's all the same. It's conservation of energy. That's what this means from this perspective. And this is the reason why Poisson was able to utilize his equation into gravity equation as well. That's very similar, it works how Einstein's equation does, only without the tensors, more differentials. That's another time for another story. So, right? Well, guess what? Here's another way to put it. Is that a GPE of a body which is moved, then restored to its original height, is conserved. So, guess what? The electric field, an electrostatic field, electrostatic field also has conservation of energy in the same thing, where it doesn't matter how you get from point A to point B. As long as you know point A and point B, you can calculate the energy needed to get to either. It's going to be equal. So, a gravitational field and an electrostatic field, which is just an electric field, an electron, just an electron sitting still, not moving at all, just sitting still, emanating its electric field around it. That's called an electrostatic field. There's no motion involved. There's no acceleration. So that is when it has conserved energy, just like a gravitational field. All right? So if we move, we find this property called curl. And the curl of a gravitational field is 0. Pretty much 0. There is no curl in a gravitational field. All right? And this is very much linked to what I'm talking about here, that it conserves energy. There is no curl in this. That's why it conserves energy the way it does. If there was curl, it would not conserve energy. So, if we go to Maxwell's equations, which define the electric field emanating from the electron, here's the equation that deals with that part specifically right here. Okay, this one deals like magnetic field, electric curl, moving electrons around with a magnetic field, vice versa. So basically, as you see, this little upside down triangle, if I'm not mistaken, I believe means like change in the system or something. So if you have change of the electric field, that's what the E stands for, and the B stands for magnetic field, and this is over time. Change over time will give you curl. If you have no change, you have no curl. This equals zero. Zero curl, which means we're right back at the electric field is conserved by nature, as is a gravitational field, which remember, which is why Poisson can apply his math the way he did. Okay? Hope you guys are with me on this far. All right? So, there's 2 points that I really want to make right now that are very important. The first one is that this absolutely is proof that dynamic gravity is correct. Because if the electric field, which is essentially the sister force of gravity, is what an electric field is, the sister force of gravity, has no curl and conserves energy, then we would expect it to be true that so would a gravitational field. It would have no curl and conserve energy, which it does. All right, that's point number 1. That is proof in a very subtle way, but yes, proof that my theory of dynamic gravity is correct. The second point is a little more mind-blowing when you think about it. So we have electrons, and we have our nucleus, I mean the protons and neutrons, right? And the electrons are emanating the electric field, blah, blah, blah. My next video is going to do a really good deep dive probably into the differences between the fields emanating from the electron versus the proton, which confuses everybody when it comes to dynamic gravity, except me. I'm the only one that never fell for the trick. But everybody else I know, they can't wrap their head around the fact that they're different. They think they're the exact same thing. My next video will show you they're not, hopefully. But I digress. So we have an electron sitting still. We have an electric field, all right? But when the electron is accelerating, according to Maxwell's equations, which we know are correct, and we can calculate a lot of stuff with this, we start to get curl, all right? And curl is kind of like in physics a right-hand rule or whatever, where if you have like, I don't know, like right-hand rule. If you have like electricity going this way in a wire, then the magnetic field will curl around it as your fingers do your palm. You know, it will be in that direction. Basically perpendicular, like 90 degrees offset of the electric field is what the magnetic field is. Kind of weird. I still can't wrap my head around that. So if you don't understand that, you're not the only one. Don't feel bad. That's my next step I'm working on. But right, so that's what curl is. Curl is when an electron is accelerating, and then a magnetic field isn't created by the disturbance of that accelerating electron, hence creating the magnetic field and 90-degree angles perpendicular to the electric field, enveloping it in an entire cylinder around it. All right? Well, according to my theory of gravity, gravity emanates from the electromagnetic force emanating from the proton. All right? But the protons aren't really moving. They're not accelerating. the electrons are. They're bouncing around all the time, releasing photons of energy and this and that. But the protons, not so much. So, in effect, I want you to think about this. This is a mind blow. Right now, there's like three forces, all right? There's the electric field, when you have an electron sitting still. There's a magnetic field that's created perpendicular to the electric field, which puts out an incredible force when the electron moves. And then you have the field of the proton when it's sitting still, which is creating gravity as we know it. So what happens when the proton accelerates like an electron? It too, in theory, would also create a 90-degree perpendicular force that would do very weird things as a magnetic field does versus an electric field. It would be related, but it's going to be different. It's going to be very weird as far as what's going on. So basically the mind blow is if you could have a bunch of moving protons, like a bunch, moving in the way that like electricity does, with electrons moving, which can create magnetic fields, electromagnets, you could also create a force that has never before been seen on this planet, which I don't even know what it would do, man. I have no clue. Would it be gravity squared? Would it affect this and not that? I don't know, man. I have no clue. I can't even guess. It's too radical for me. It's too radical of a thought. But this is absolutely predicted by dynamic gravity. So maybe one day we'll be able to get enough protons spinning to measure this force. With the protons at like CERN traveling like almost the speed of light, man, there's just not enough of them to really measure anything. I mean, in equivalence, that would be like equivalence, like what, a millionth of a volt, of electricity. And so you're going to have like a millionth of whatever this new force is. It's so minuscule, and they don't even know to look for it. They don't even know. But, I mean, theoretically, they might be able to detect it somehow. Maybe some of these particles that they see at CERN are caused directly from this force. I don't know. Maybe one day we'll get there. Unfortunately, I fear not in my lifetime. But it is definitely a very interesting experiment that if we could ever do. But protons, are like the most reactive thing in the world. Pretty much, if you just have like a single proton, you have like the world's most powerful acid. It will just dissolve and eat away anything it touches. And there's nothing that can resist it. Like not even a noble gas, It's just like, nope, it's going to eat everything. So there's that. I hope you learned something today about how to get through walls that life presents you, and a few things about gravity and what's going on. Look out for my next video. I'm really going to dive deep into the forces of the electromagnetic force and hopefully squash all these haters that want to think that, my theory of dynamic gravity is nothing more than the electric field. It's not. It's different. It is different. But until then, I hope you guys have a great day. Thank you for staying with me, and bye-bye.
Like, subscribe, submit.